Hi everyone, I am Rohit Mohanty and today I'll be talking about spectral graph theory and its relationship to some of the problems related to graph structure. So I will begin by introducing some of the basic concepts of spectral graph theory, and then I will talk about some well-known problems about graph structure, which are the graph coloring problem and the independent sets problem. I will then use Hoffman's bound to find the upper bound on the independence number and the lower bound on the chromatic number of a graph. Then I will talk about the graph partitioning and Cheeger's inequality. And finally, I will conclude by talking about planar graphs and some of their properties that relate to the spectral graph theory. So let's begin. As we all know that the spectral theorem states that if M is an n by n matrix which is real and symmetric, then there exist real numbers lambda 1 to lambda n and n mutually orthogonal unit vectors psi 1 to psi n such that psi I is an eigenvector of M of eigenvalue lambda I for each I. Now we will discuss the relationship between the eigenvalues of Laplacian and adjacency matrix to different problems related to graph structures. But before that, we will talk about the eigenvalues of Laplacian and adjacency matrix. So the eigenvalues of the Laplacian matrix are actually arranged in increasing order, where lambda 1 is the smallest eigenvalue and lambda n is the greatest eigenvalue. Lambda 1 is also equal to 0. But the adjacency matrix eigenvalues are arranged in decreasing order. So mu1 is the greatest eigenvalue of the adjacency matrix and mu n is the smallest eigenvalue of the adjacency matrix. There is also a relationship between the eigenvalues of the Laplacian matrix and the adjacency matrix, which is given by mu I is equal to d minus lambda I. Now that we know this, let's start by discussing one of the problems about graph structure, which is the graph coloring problem. The graph coloring problem essentially has two goals. The first one is to assign a color to every vertex in the graph such that none of the adjacent vertices have the same color. And the second goal is to use as few colors as possible to accomplish this task. Now a graph is called k-colorable if we can use at least k colors to completely accomplish the task that was mentioned above. And the chromatic number chi g of a graph is the least value of k for which a graph g is k colorable. Now as we can see in this picture, none of the adjacent vertices have the same color. Therefore here the task has been properly accomplished. Another neat property about the k-colorable graphs is that a two-colorable graph is a bipartite graph. Now the thing is, what is a bipartite graph? A bipartite graph is essentially dividing the graph, a graph in which we can divide the vertices into two subsets, and any of the vertices in one of the subsets do not have any edge between them. So none of the vertices in either of the subsets have any edges between them, which is essentially what two colorable means. Two colorable also means that we can assign two colors to the end to all of the vertices, one of the two colors to all of the vertices in a graph such that none of the vertices that have been assigned the same color have any edges between them. Also, a four-colorable graph is a planar graph. Now we move on to describe another problem, which is the problem of independent sets. A set of vertices S is independent if there are no edges between the vertices in S. So this essentially means that we want to find a set of vertices such that there is no edge between any of the vertices in the set. Now each color class in a coloring problem is an independent set. Now this is quite evident because when we assign a coloring class to a vertex, we make sure that it does not have any edge with any of the other vertices that have been assigned to the same coloring class. Therefore all the vertices in a coloring class will form an independent set. Now the independence number alpha g is the size of the largest independent set in a graph. So this is pretty straightforward, and since a k colorable graph with n vertices must have a color class of size at least n by k, therefore alpha g is greater than or equal to n by chi g. Now this is also pretty straightforward, because as we are saying that the size of a color class must be at least n by k. So therefore this alpha, that gives us a lower bound on alpha g, that is alpha g is greater than or equal to n by chi g. So now that we have defined these two problems, let's move on to find the bounds on the independence number and the chromatic number. So for that we will use Hoffman's bound. Now Hoffman's bound was one of the first results in spectral graph theory. Hoffman's bound provides an upper bound on the size of an independent set in a graph G. Now Hoffman's bound was initially introduced for a d-regular graph. So let me first explain what a d-regular graph is. A regular graph is a graph that has where the degree of every vertex is equal. That is, every vertex in the graph has the same degree. And a d-regular graph is a graph where every vertex has degree equal to d. So now let's go over the theorem and see what it says. So the theorem says that if G is a graph with the set of vertices as V and the set of edges as E, and if it is a d-regular graph, and if mu n is the smallest adjacency matrix eigenvalue, then alpha g is less than or equal to n multiplied by minus of mu n divided by d minus mu n. Now one thing to note here is that there is a negative value on the numerator, but that is alright, because mu n is, since it is the smallest eigenvalue of the adjacency matrix, so mu n is less than 0. Therefore RHS overall is going to be positive, and therefore alpha g is going to be positive. The bound on alpha g is going to be positive. So this gives us a bound on the alpha g for a d-regular graph. But we want to generalize this theorem, and the generalized version of this theorem was given by Goertzel and Newman. So let's go over the generalized version of Hoffman's theorem. Now that theorem states that if S is an independent set in G and d average of S is the average degree of a vertex in S, then mod S is less than or equal to n multiplied by 1 minus d average S upon lambda n. Now this gives us a generalized case of the previous theorem. This is because, and this can also be reduced to the specific previous theorem to the case of d-regular graphs. In order to reduce it to the case of d-regular graphs, what we can do is we can substitute the values appropriately. That is, for d average we can substitute d, because in the case of d-regular graphs the d average of all the vertices is going to be d, and that is because every vertex is going to have a degree of d, and the d average is calculated as the sum of all the degrees divided by the total number of vertices. So the d average is ultimately going to be n into d upon n, where n is the number of vertices in that set. So it's ultimately going to be d. And as we already know that lambda n is equal to d minus mu 1. So these bounds are the same for the regular graphs, and we are going to substitute these values in this equation, which will give us that 1 minus d average S upon lambda n is equal to lambda n minus d, because lambda n, if we just take lambda n to the numerator and then replace d average by d, and this value is equal to negative of mu n, and the denominator is equal to d minus mu 1. So this is exactly the same as the special case, as the d-regular case of Hoffman's theorem. So we can derive the special case from the general case. Now that we have seen Hoffman's theorem for the generalized Hoffman theorem, let's apply it to a special graph and see the bounds on that special graph, which is called a Paley graph. Now, first let me define what a Paley graph is. The Paley graph of order P, where P is a prime power, is a graph on P nodes with two nodes adjacent if their difference is a square in the finite field. Now, the graph is going to be undirected when P belongs to the equivalence class of 1 mod 4. And below are a few examples of Paley graphs. So as you can see, these are some this is a 17 Paley graph and this is a 13 Paley graph. So all of these orders of Paley graph are prime powers. So now we will apply Hoffman's bounds on Paley graphs and see what its effect is. If G is in order to apply that, if G is a Paley graph and S is an independent set in that graph, we have we have to substitute N with P, and D will be equal to P minus 1 by 2 and lambda N will be equal to P plus root P by 2. So Hoffman's bound will tell us that from the general expression for Hoffman bound, we know that mod S is less than or equal to N into 1 minus D average S upon lambda N. So if we substitute these values, we will get mod S is less than or equal to root P. It will simplify to this nifty need value. So essentially we have found a bound on the size of the independent sets of Paley graphs. Now let's talk about the chromatic number and the effect of Hoffman's bound on chromatic number. Now, as a k colorable graph must have an independent set of size at least n by k, an upper bound on the size of independent sets gives us automatically a lower bound on its chromatic number. However, this bound is not that good and it requires the graph to be regular. But Hoffman proved the following lower bound on the chromatic number of a graph, and that does not require the graph to be regular. So that bound was chi g is greater than or equal to mu1 minus mu1 upon negative of mu1, and that is equal to 1 plus mu1 upon negative of mu1. Now this gives us a lower bound on the chromatic number of any graph. There is also a neat relationship for block partitioned symmetric matrices that is worth knowing. If M is a block partitioned symmetric matrix with k greater than or equal to 2, then k minus 1 into lambda minimum of M plus lambda maximum of M is less than or equal to the sum of MII or lambda maximum of MII. So here lambda minimum is the smallest eigenvalue of the Laplacian of M and lambda maximum is the greatest eigenvalue of the Laplacian of M. Now that we have these neat results about the lower bound and the upper bound of different graph properties, now let's talk about another problem, which is the graph partitioning problem. The graph partitioning problem is essentially the reduction of a graph to a smaller subgraph by partitioning its set of nodes into mutually exclusive groups. Edges of the original graphs that cross between the groups will produce edges in the partitioned graph. Now, if the number of resulting edges is small compared to the original graph, then the partitioned graph may be better suited for analysis and problem solving than the original graph. Now, as we can see in this picture, this is the original graph, and we have partitioned it into two different subgraphs, and these are the edges in between these two subgraphs, which will serve as the edges for the new partitioned graph. So here we will examine the isoperimetric ratio and the conductance of a graph, and how they are related to the second smallest eigenvalue of the Laplacian and the normalized Laplacian. Now let's talk, before talking about isoperimetry, let's talk about the boundary of a subset of a graph. Now if S is a subset of the vertices of a graph, then the boundary of S can be defined as the number of edges connecting S to the rest of the graph. Formally, boundary is defined as del S equal to the set of edges AB such that A belongs to S and B does not belong to S. Now this gives us a way of measuring how well S can be separated from the graph. Also, the isoperimetric ratio can now be defined as the ratio of the boundary of S to the size of S itself. That is, theta S is defined as the size of del S upon the size of S. Now, the isoperimetric ratio of a graph is the minimum isoperimetric ratio over all sets of at most half the vertices. That is, theta G is defined as the minimum of theta S, where mod S is less than or equal to n by 2. Now let's talk about the lower bound on the isoperimetric ratio. To get that, we have a theorem that states for every S that is a subset of V, theta S is greater than or equal to lambda 2 into 1 minus S. Here lambda 2 is the second eigenvalue of the Laplacian of the graph, and S is given by the ratio between the size of the subset upon the size of the total size of the vertices of the total graphs. Now in particular, theta G is greater than or equal to lambda 2 by 2. Okay, this theorem says that if lambda 2 is big, then G is very well connected. That is, the boundary of every small set of vertices is at least lambda 2 times something just slightly smaller than the number of vertices in the set. Now if we rearrange the terms in this equation, then we can also state that theta S can be written as mod V into mod of del S upon mod S into mod V minus S, and that is greater than or equal to lambda 2. Now let's talk about another property of a graph, which is called conductance. Conductance of a graph measures how well knit the graph is. It controls how fast a random walk on a graph converges to its stationary distribution. The formula for conductance is derived by an appropriate normalization of the isoperimetric ratio for the weighted graphs. Instead of counting the edges on the boundary, we can count the sum of their weights, and similarly the denominator depends upon the sum of the weighted degrees of the vertices in the S. Formally, the conductance can be defined as phi S is defined as W of del S upon minimum of ds and dv minus S. Here ds is the degree of vertices in S, and for a set of edges F, Ws is defined as the sum of weights of edges in F. So now conductance can also be rewritten as phi S, which is defined as dv into W of del S upon ds into dv minus S. Now the conductance of a graph is defined as phi g equals minimum of phi S for all S that is a subset of V. That is, we pick the subset with the minimum conductance, and that is the conductance of the entire graph. Now the conductance of a graph is more useful when we are concerned about edges, and the isoperimetric ratio is more useful when we are concerned about vertices. The conductance is particularly useful when studying about random walks in graphs. Now let's talk about another important matrix, which is the normalized Laplacian. Let's consider the following generalized Rayleigh quotient, which is y transpose Ly upon y transpose dy. If we substitute x is equal to d to the power 1 by 2 y, then this ratio becomes x transpose d to the power minus 1 by 2 L d to the power minus 1 by 2 x upon x transpose x. Now this matrix in the middle is called the normalized Laplacian, which we can formally define as n is equal to d to the power minus 1 by 2 L d to the power minus 1 by 2. Here L is the Laplacian matrix. Also, the eigenvalues of n are nu1 to nu_n, where nu1 is the smallest eigenvalue and nu_n is the greatest eigenvalue, and nu1 is equal to 0. Now let's talk about the eigenvalues of n. the eigenvalues of the eigenvector of eigenvalue 0 of n is d to the power 1 by 2. Now this refers to the vector whose entry for the vertex u is the square root of the degree of u. Now the eigenvector of nu2 is given by arg minimum of x transpose nx upon x transpose x for all x which are perpendicular to d to the power 1 by 2. Now this makes sense because nu2 is essentially the second smallest eigenvalue of n. Since nu2 is the second smallest eigenvalue, we try to find the smallest eigenvalue which is perpendicular to the first eigenvector. So the first eigenvector is d to the power 1 by 2, and we try to find the eigenvector which is perpendicular to that out of all eigenvectors which are perpendicular to that eigenvector. We try to find the smallest one. We can also substitute x back to y, so in a way that x transpose d to the power 1 by 2 becomes y transpose d to the power 1 by 2 into d to the power 1 by 2, which is y transpose d. Therefore we have nu2 is equal to minimum of y transpose ly upon y transpose dy for all y which are perpendicular to d. So now let's discuss about the lower bound on the conductance of a graph. So the conductance is related to nu2 as the isoperimetric number is related to lambda 2. So this gives us that the conductance of a graph is greater than or equal to nu2 by 2. And since the conductance of a graph is essentially the minimum value that the conductance of S can be, which is the conductance of any subset of the graph can be, so therefore the conductance of any subset of a graph is greater than or equal to nu2 by 2. So far we have talked about the lower bound on the conductance of a graph. Now let's talk about the upper bound on the conductance of a graph, which is given by Cheeger's inequality. Now Cheeger's inequality relates the eigenvalues of the normalized Laplacian matrix to the conductance of S and gives us an upper bound for it. So Cheeger's inequality basically says that there exists a set of vertices S for which phi S is less than or equal to root over 2 nu2. Cheeger's inequality proves that if we have a vector y orthogonal to D for which the generalized Rayleigh quotient is small, then one can obtain a set of small conductance from y. We obtain such a set by carefully choosing a real number tau and setting S tau equals A, the set of all A, such that ya is less than or equal to tau. Now before moving forward, let's discuss what a centered vector is. A vector y is centered with respect to D if D is the sum of all dA for all A such that ya is greater than 0 is less than or equal to dV by 2, and the sum of all dA such that for all A such that ya is less than 0 is also less than or equal to dV by 2. Now if psi2 is an eigenvector of nu2, then y is equal to d to the power 1 by 2 psi2 is orthogonal to D and the generalized Rayleigh quotient of y with respect to L and D equals nu2. But the theorem can make use of any vector that is orthogonal to D that makes the generalized Rayleigh quotient small. In fact, we prefer vectors that are centered with respect to D. By renumbering these vertices, we may assume without loss of generality that y1 is less than or equal to y2, and which is less than or equal to y3, and so on, and yn is the greatest value. Now to center y, let j be the least number for which dA, the sum of all dA for a from 1 to j is greater than or equal to dV by 2. Now we can set z equals y minus yj into 1, where 1 is an all ones vector. Now this vector z satisfies zj is equal to 0, and we can show that Z transpose LZ upon Z transpose DZ is less than or equal to Y transpose LY upon Y transpose DY. Now let's discuss a theorem that can actually give us an upper bound on the conductance of S tau. This theorem states that if G is a weighted graph and L is its Laplacian and D is its vector of weighted degrees, then let Z be a vector that is centered with respect to D. Then there is a number tau for which the set S tau is equal to A such that for every ZA is less than tau satisfies the conductance of S tau is less than or equal to root over 2 into Z transpose LZ upon Z transpose DZ. Now this essentially gives us what we wanted, which is an upper bound on the conductance of the S tau of a graph. So now that we have talked about all of these properties related to the structure of the graph and all of these various properties related to normal graphs, let's talk about some special kinds of graphs which are called planar graphs. Let's first begin by describing planar graphs. A planar graph is a graph that can be embedded in the plane. That is, it can be drawn on the plane in such a way that its edges intersect only at their endpoints. In other words, it can be drawn in such a way that no edges cross each other. Planar graphs are the graphs that do not have K5 or K33 minors. Now, what is a K5? A K5 is a complete graph with 5 vertices, and a K33 is a bipartite graph with 3 vertices on each end, on each side. Now, any graph that is non-planar has either K5 or K3 or both as its minors. But any graph that does not have these two graphs as their minors are called planar graphs. And it can be proved that they are planar graphs. Now there is another interesting property that 3 connected planar graphs are the skeletons of 3-dimensional convex polytopes. Now moving on to a few interesting relationships between the planar graphs and spectral graph theory. So here we will talk about an upper bound on the second eigenvalue of its Laplacian. So if G is a planar graph with n vertices of maximum degree d, and lambda 2 is the second smallest eigenvalue of its Laplacian, then lambda 2 is less than or equal to 8d by m. This clearly shows that for planar graphs, the second smallest Laplacian eigenvalue is small. We can then use Cheeger's inequality that we learned just now to prove that the corresponding eigenvector provides a good cut. Now we move on to another important matrix, which is the generalized Laplacian matrix. The generalized Laplacian matrix M of a graph G can be expressed as M equals L plus D, where L is the Laplacian matrix of the weighted version of G and D is an arbitrary diagonal matrix. Now that is, here we have imposed some restrictions which are as follows. Mij is less than 0 if Ij belongs to the set of edges E. Mij is equal to 0 if Ij does not belong to E and I is not equal to J, and Mii is arbitrary. Now we talk about another property of planar graphs, which is the Collin-de-Verdier graph parameter. The Collin-de-Verdier graph parameter is denoted as CDVG, and it is the maximum multiplicity of the second smallest eigenvalue of a generalized Laplacian matrix of a graph G that satisfies the following condition, which is for every non-zero n by n matrix X such that Xij is equal to 0, for I equal to J and Ij belongs to E, Mx is not equal to 0. This property is called the strong Arnold property. Now Collin-de-Verdier proved that the CDV G is at most 2 if and only if the graph G is outer planar. Outer planar means that it is a planar graph in which every vertex lies on one face. Now he also proved that it is at most 3 if and only if G is planar. Also, Lovász and Schrijver proved that it is at most 4 if and only if the graph is linkless embeddable. Now we come to the end of my part of the presentation, and I would like to conclude by saying that we saw various results that showed the significance of spectral theorem on various problems related to graph structure. In particular, we discussed the impact of the spectral graph theory on graph coloring problem, independent sets problem, graph partitioning, and Cheeger's inequality. And we also saw some neat properties of planar graphs that related to spectral graph theory. Now, these results gave us really significant insights into various properties of the graphs and are really important in this field. Now I pass on the floor to my teammate Sudata, who will be talking about error correcting codes and expander graphs. Thank you for your time.
Hi, I'm Sudata Hor, and I'm going to be talking about error correcting codes using expander graphs. So, a quick rundown of the presentation. First, I'm going to talk about an introduction to coding theory, and I'm going to explain what bipartite expander graphs are, because this is an essential ingredient into our construction of these error correcting codes. Then I'll talk about the actual construction of these codes, and then prove some performance on the codes. So first, let's talk about an example problem of error correcting code. First, let's state the problem. Let's say Alice wants to send Bob a binary string. Let's say 0101. But there's going to be interference in the transmission of this message. One bit will be flipped, so Bob might receive 1101. And the problem for Alice, the problem that we want to solve, is what can Alice send so that Bob can always figure out what the true message is. And a basic solution to this is to just send each bit 3 times. This way, if there's only one error, Bob could just take a majority vote on these bits and recover the true message. But if there's 2 errors, this actually doesn't work, and this code turns out to actually be inefficient. So what we want to do is to find a better error correcting code, and in this presentation we'll talk about using expander graphs to construct something called expander codes. And what we use is a bipartite expander graph and a linear code. Both of these we'll define later in the presentation. But first, let's define what a code formally is. We formally define it to be some mapping from strings of length m to strings of length n. We can think of strings of length m as the original message, and then the strings of length n as the encoded message. And then we call a code word to be an element in the image of C. And then just note for the rest of the presentation, we might abuse notation and say that C is actually the image of C. And something else that's useful to define is the rate of C, which is m divided by n. And in our earlier example, when we send each bit 3 times, the length of the original field would be like 4 bits, and then the length of the encoded field would be like 12 bits. So the rate would be 1/30. Okay, next we will define the Hamming distance between 2 code words. And this is really simple. It's just the number of bits that 2 codes differ by. And we also are interested in the minimum distance between these 2 codes, because a large minimum distance is good. We can correct any number of errors less than d/2. And an intuitive analogy is considering, let's just consider the xy plane. And let's say we're running like k-nearest neighbors. We have 2 points, 1 and 2. And then we have some like message and error. And let's say we're running like k-nearest neighbors, right? And the distance between these 2 would be d. But if the error message is actually right in between the 2 codes, then we can't decide which one is the nearest neighbor. And it's also helpful to define the minimum relative distance as delta equals d over n. All right, so I'd like to clarify the analogy earlier because I think the first time was a little bit unclear. So we're working in the two-dimensional plane. Let's say the closest code words are x and y. This means the minimum distance is just the distance between these 2 points. Okay, and when we transmit a message, the messages are going to look like this. They're going to be elements of these circles. All right, so if we want to send x, it's just going to be x plus some error, and if we want to send y, it's going to be y plus some error. So if epsilon is less than the minimum distance divided by 2, then we can have these circles that are non-intersecting. So if the message is in y, then it will not be in the set of x. But let's say the number of errors is greater than d over 2, right? So then we will have something that looks like this. So we have intersecting circles, and let's say we have a message in the intersection that we can't tell which set it belongs to. We can't tell if the center should be x or should it be y. This means that we can correct any number of errors that is less than d over 2. Next, we also define a linear code, which is actually one of our fundamental ingredients in constructing these expander codes. So this is just a code whose code words satisfy MC equals 0, where M is just some matrix of dimensions n minus m by n. And we can think of n minus m as like the number of constraints. And of course, n is the length of our encoded message. Okay, next we will define a generated matrix for this linear code. Every linear code has a useful generator matrix where if we just have any original message B, the encoded message for that will just be GB. So here's an example of a linear code. We define a matrix M as follows, and then the Hamming code is known as the set of all C that satisfies MC equals 0. So to encode it is our original messages are going to be just 4-bit strings, all right? And what we do is we set the 4 bits in C, the first 4, as our message, and then these next 3 are going to be defined by MC equals 0. All right, and we can notice if there is 1 bit flip, then each column of M is different, so we can tell which bit is flipped. All right, next let's talk about bipartite expander graphs. First, let's define what an expander graph is. You can think of it as a well-connected sparse graph, but formally, a deregular graph is an epsilon expander graph if each adjacency matrix eigenvalue mu satisfies the absolute value of mu is less than or equal to epsilon d. So an easier way to think of it is expander graphs are approximations of complete graphs. In other words, the graph where each pair of vertices are connected by an edge. And it's important to note Tanner's theorem, where expander graph gets its name from. Essentially, like each small set of vertices have a large number of neighbors. And what Tanner's theorem states is that if we have any set of vertices S, then we can always find this lower bound on the number of neighbors of S. Next, we will define a bipartite graph. It's a graph whose vertices can be divided into two disjoint and independent sets U and V. And we also define a complete bipartite graph to be a bipartite graph where each vertex in U is connected to a vertex in V. So the example below, we could have the bottom set, the blue set, to be U, and then the top set to be V, and then each vertex in U is independent to another vertex in U, and then each vertex in V is not connected to another vertex in V, but each vertex in U is going to be connected to each vertex in V, and that's what makes it complete. So just like how earlier we said expander graphs approximate complete graphs, we can also say bipartite expander graphs approximate complete bipartite graphs. Next, we'll state a fundamental theorem that we will use later on to prove convergence. Let's say we have a bipartite expander graph, and we take any set of vertices S and U, and any set of vertices T and V. And then we could find an upper bound for the average degree in the union of S and T. All right, so now we defined what a bipartite expander graph is. We can actually construct our expander codes. So formally, let's denote the expander code with C. And recall earlier we stated we use bipartite expander graph and a linear code. So let G be the deregular bipartite epsilon expander graph on 2n vertices, and let C naught be our linear code of length D. So we think of C naught as a small linear code of small constant D, and this is going to be our building block, and we're using a graph to basically expand C naught and scale it up to be efficient. And let's talk about what code words look like. So in our graph G, each edge in this graph is going to be 1 bit. And there's going to be dn edges because we have 2n vertices, and each vertice has d edges. So there are dn edges in total. So there's dn bits. And we can denote all of these bits by y sub 1, y sub 2, and so on. And we also want to add a constraint onto each code word. So given any vertex in G, let's say we have d edges attached to that vertex, and we're saying that each bit associated with that edge will have to be a code word in C naught. So B1, B2, B3, B4, B5 is going to be an element of C naught. Okay, and also note that order doesn't matter, but it should be fixed. All right, now let's talk about how we can actually encode, right? Before we talk about encoding, we should think about the rate of this code. So let's say R naught is the rate of our original code C naught, and if we remember the definition of a rate is actually m over n, and for C naught, in this case, n will be d, so the original message length will be m equals r naught times d. So this is actually representing the space of our code words, because if we have r naught d number of possible messages, then there are r naught d number of code words. Since C naught is a linear code word, we have the matrix M that has, let's say, remember it's n minus m by n matrix. And then this basically tells us how many constraints we have. And then if we expand it to the bigger graph, we just multiply by 2n. So we have this many total linear constraints. And then the vector space of all code words that satisfy these constraints will then be dn minus number of constraints. We find the dimension of the code words, and this is actually equal to the rate times the number of code words, or the length of code words, sorry. And this is how we can actually determine the rate of C. So with this rate, there's an underlying matrix, like as we stated earlier. It's n minus m, this right here, by n. And the code words of C are precisely vectors y that satisfy my equals 0. And of course, it's a linear code, so we can find, using linear algebra, a generated matrix G with these dimensions. And encoding would just be applying this generated matrix G. So next we could talk about a decoding algorithm. And the concept is we start with the decoding algorithm for C naught. We call it A. And we are going to apply A to all the vertices in U first. And then we're going to apply it to all the vertices in V. And then we're going to repeat until we produce a code word in C. So next we will prove this decoding will actually converge, and we'll actually prove the number of errors that we can actually correct. So first we need to start off with a lemma. So assume that epsilon is less than or equal to delta naught over 3. Remember, delta naught is the minimum relative distance of C naught. And we say for any set of edges f, we're going to let S be a subset of vertices in U attached to the edges in F, and then we let T be the subset of vertices in V that's attached to at least delta naught D over 2 edges in F. Then we can get this following inequality of the number of vertices in T and the number of vertices in S. Okay, so the proof of this is we start out. So we're given that the size of f is upper bound or lower bounded by this quantity here, and then we think about the average degree in S union T. Okay, this is twice the number of edges in the subgraph divided by the number of vertices. So using this, we can find a lower bound for the average degree of S union T, and then remembering our earlier theorem for expander graphs, we can actually find an upper bound for the average degree of S union T. So then we get the following result in equation 2. And then now we use the fact that epsilon is less than or equal to delta naught over 3. And this gives us our final result after some algebraic manipulations. So our second lemma is an application of our first lemma, but now we're applying it to our decoding algorithm. So we start off with a set of edges in F, and instead of saying S is just some arbitrary set of vertices, now we're saying it's actually our set of vertices in U that are in error. And then this happens after a U decoding step. So next we apply a V decoding step and let T be the set of vertices in V attached to edges in error afterwards. Then we can get the following result, because all we have to notice is that T, the set of vertices, after a V decoding step must be attached to at least this many edges in F. And that just goes by definition of delta naught D over 2. That is the minimum distance of our C naught code. So delta naught D is our minimum distance. And then we can correct up to delta naught D over 2. Alright, next we move on to our main theorem, which is the decoding algorithm can correct up to this many errors and converge in a logarithmic number of iterations. So let's start out with f, the set of edges that are initially in error. We apply the first U decoding step, and then we let S be the set of vertices with edges in error. So each vertex in S must be adjacent to at least delta D over 2 edges in F. And if we assume this condition right here, then after some manipulations, we can find a lower bound on the set of S. And then by our earlier lemma, this will imply that we get a lower bound on T, which is the number of edges in error after our V decoding step. So doing this, we can show that it will converge in logarithmic number of iterations. Alright, next let's wrap up what we've covered today. So we talked about small error correcting code, C0, and it's a small size D, but it might not be efficient if we scale it up. So using expander graphs, we can actually build efficient, larger error correcting codes of size Dn. We just encode using a generating matrix G, and we decode just by iteratively applying the existing decoding algorithm A. And we notice that the number of errors we can correct scales linearly with n, while the number of iterations scale logarithmically with n. So that's all I have for today. Thank you for listening to my presentation, and I hope you enjoyed.